Hello, in this video I'd like to talk about Lewis structures. You'll recall that a Lewis structure is a symbolic representation of a molecule that shows nuclei and core electrons as element symbols, shared electron pairs as hyphens or dashes between the element symbols, unshared or lone electron pairs as dot pairs on the atom. Here's how you draw a Lewis structure. Begin by counting the total number of valence electrons in the molecule. Draw a skeleton structure using pairs of electrons for bonds. A general rule is that carbon always forms 4 bonds. The exceptions would be in small molecules or ions like carbon monoxide or cyanide, where it really can't form 4 bonds. The less electronegative element is almost always in the center. If it is a ABX type molecule with a single atom of one element and 2 or more atoms of another element, it's usually symmetrical with A in the center and the B atoms attached to it. You then distribute the remaining valence electrons as lone or unshared pairs on the atoms in order to satisfy the octets of all atoms. And you'll recall that the octet rule says that in stable molecules, all atoms achieve filled valence shells by sharing electrons with other atoms, and for most elements, that corresponds to 8 electrons, corresponding to 2 in the S sublevel and 6 in the P sublevel. So, let's do some Lewis structures. PH3, phosphine. Oh, did you know that phosphine is the molecule that was just discovered in the atmosphere of Venus, and they think that that might be a sign of some sort of life on Venus, which is really amazing. Anyway, PH3 is phosphine. I'll count the valence electrons. 5 from phosphorus, 1 from each of the 3 hydrogens is 8 valence electrons. And in order to satisfy everyone's octet, phosphorus is in the center. It forms 3 covalent bonds to hydrogen with 1 lone pair. In selenium difluoride, I have 20 valence electrons. I form bonds to the 2 fluorine atoms from the selenium, distribute the remaining valence electrons as lone pairs to satisfy the octets of selenium and the 2 fluorine atoms. In O2 and HCN, which have 12 and 10 valence electrons respectively, the only way to satisfy everyone's octet is by using multiple bonds, which I'll talk about in a second. So in O2, there are 2 covalent bonds, that is a double bond between 2 oxygen atoms corresponding to 4 shared electrons. Each oxygen then has 2 lone pairs on it to satisfy their octets. In HCN, hydrocyanic acid, by the way, the order of connectivity is given as it is typed, so hydrogen attached to carbon attached to nitrogen. We have a single bond between the hydrogen and the carbon, a triple bond between carbon and nitrogen with a lone pair on the nitrogen. We can also draw Lewis structures for polyatomic ions. SO42-, the sulfate anion, is a group of nonmetallic elements held together by covalent bonds, but 2 additional valence electrons needed to be added in order for it to be stable. The only modification is that, well, one of the modifications is that when counting the valence electrons, you have to account for the charge. For each negative charge on the polyatomic ion, add an additional valence electron. For each positive charge, subtract 1. That gives us 32 valence electrons in sulfate. I will satisfy sulfur's octet by forming 4 SO bonds, distribute the remaining valence electrons as lone pairs. The only other difference for polyatomic ion is that by convention, after you draw the Lewis structure, you put square brackets around it with the net charge to the upper right. So what is a multiple bond? As I said before, it is more than one shared pair of valence electrons. So the question is, how does the bond length or bond distance vary as you increase the number of bonds? Well, let's look at some data and see if we can explain it. We can see that as we go from a carbon-carbon single bond to a carbon-carbon double bond to a carbon-carbon triple bond, the measured bond length in picometers decreases noticeably. We can explain that by saying that when there are more shared electrons, there is greater electrostatic attraction among the oppositely charged particles, that is the negatively charged electrons and the positively charged nuclei. So more shared electrons simply means that the nuclei are going to be held more closely together. What about bond energy? Remember, bond energy is the energy that's required to break the bond. Well, if we look at these single, double, and triple bonds, we can see, as we might expect, that as we increase the number of shared electrons, we increase the bond energy. Once again, more shared electrons means greater electrostatic attraction, more energy is released when the bond is formed, and correspondingly more energy is needed to break the bond. So going from single to double to triple bond, the bond length gets shorter, the bond energy gets greater. Here are some exceptions to the octet rule. Obviously, hydrogen cannot have 8 electrons around it. Its valence shell consists of just the 1s orbital, which can only hold 2 electrons. So the only thing you'll ever see hydrogen do in a Lewis structure is form one single bond. It will never form a multiple bond. It will never form 2 bonds. It can never have a bond in a lone pair. Beryllium and boron, probably because they're very small, they can form compounds in which that atom has fewer than 8 electrons. And finally, molecules with expanded valence shells, which can occur if the central atom is in the third period or lower on the periodic table. Okay, so let's do some examples of that. Let's draw Lewis structures for phosphorus pentafluoride, sulfur tetrafluoride, chlorine trifluoride, and the tribromide anion, Br3, with a single negative charge. In phosphorus pentafluoride, I have 40 valence electrons. The only way I can do this is by having the phosphorus in the center, forming 5 covalent bonds, one to each of the fluorines, and each fluorine having its octet satisfied with 3 lone or unshared pairs of electrons, for a total of 40 electrons. In sulfur tetrafluoride, I have 34 valence electrons. Sulfur is in the center. It forms bonds to each of the 4 fluorine atoms, but we must put an additional lone pair on the sulfur in order to accommodate that last pair of electrons. So in sulfur tetrafluoride, sulfur is forming 4 covalent bonds with a remaining lone pair in its valence shell. Chlorine trifluoride has 28 valence electrons. Similarly, it will form 3 bonds to the fluorine atoms, and with 2 remaining lone pairs in its valence shell. The tribromide anion has 22 valence electrons. We have a linear arrangement, and in order to accommodate all of those valence electrons, the central bromine atom has 3 lone pairs on it. Now, let's look at sulfur dioxide. If I draw a Lewis structure for sulfur dioxide, I will see that I have 1 sulfur-oxygen single bond and 1 sulfur-oxygen double bond. That would seem to imply that there are 2 different types of sulfur-oxygen bonds in this molecule, one shorter, stronger SO double bond, one weaker, longer SO single bond. But that's not the case. Okay? Studies show that the 2 SO bonds in sulfur dioxide are actually equivalent in both their energy and in their distance. That must mean that the model is flawed. And for many molecules, it is actually flawed. The Lewis structure model simply doesn't work because I could equally well have drawn another structure in which the SO double bond was on the left and the SO single bond was on the right. When you observe this, when you see that more than one Lewis structure can be drawn for a molecule, we say the molecule exhibits resonance. Resonance occurs when more than one Lewis structure can be drawn. It occurs when the electrons are delocalized. Okay? So in order to patch the flawed model, we're going to show all possible arrangement of electrons. And keep in mind that the actual structure is not one or the other, but the average of the 2. And you may also recall that our convention is that we, after drawing our resonance structures, we do a double-headed arrow to link them together to show that they are in resonance. Okay? Now, because in sulfur dioxide, the number and types of bonds are equal, each one has 1 SO double bond and 1 SO single bond, we say that they are equivalent resonance structures, and each contributes 50%. So the SO bond in sulfur dioxide would really be best thought of as not a single bond or a double bond, but 1.5 bonds. And in fact, if you look at the structure, you will see that the SO bond length in sulfur dioxide is intermediate between that of a legit SO single bond and a legit SO double bond. Now, as I said, in sulfur dioxide, these are equivalent resonance structures. But what if the resonance structures aren't equivalent? What if you're looking at 2 or more resonance structures that have differing numbers of bonds? How are you going to judge which is the more important resonance contributor, as we say? Or in the weighted average of the resonance structures to come up with the actual structure, which one contributes the most? Okay? To do that, scientists came up with the concept of formal charge. Formal charge is a positive or negative charge assigned to an atom in a resonance structure. And it tells you the relative charge on that atom in that particular resonance structure compared to the neutral atom. Okay? So if there's a positive formal charge, that means there's a deficiency of electron density compared to the free atom. If there's a negative formal charge, it means there's a buildup of electron density compared to the neutral atom. And here is how you calculate the formal charge. You take the number of valence electrons on the free atom from the periodic table, and you subtract the number of valence electrons that are assigned to that atom in that particular resonance structure. And that is simply all of the unshared electrons plus half the shared electrons. So you assign to an atom in the resonance structure all of the lone pair electrons plus half of the shared electrons. Okay? And once you've done that for all resonance structures, The most important resonance contributor, the one that is closest to reality, is the one that minimizes charge separation, so the one that has the least formal charge. But if you can't avoid formal charge, it's the one that puts the negative formal charge on the more electronegative atom, which makes perfect sense. So let's see an example of how this works. We're going to look at the cyanate anion, which has the formula OCN-. We're going to write all possible resonance structures. We're going to assign formal charges to all atoms in each resonance structure, and based on those and the criteria just mentioned, choose the one that we're going to say is the most important resonance contributor, and then based on that, describe what the OC and CN bonds look like. So I'm going to do all three in random order. The total number of valence electrons is going to be, I believe, 16. 6 plus 4 plus 5 plus 1, yeah, 16 electrons. Okay, so in the first one, I'm going to draw a carbon-oxygen double bond and a carbon-nitrogen double bond. That accounts for 16 electrons, and everyone's octet is filled. Oxygen, 6 valence electrons on the free atom, minus the 4 unshared electrons, plus half of the 4 shared electrons. So 6 minus 6 gives me a formal charge of 0. For carbon, 4 electrons on the free atom, minus 0 unshared electrons, plus half of the 8 shared electrons, gives me a formal charge of 0. Looking pretty good so far. Nitrogen, 5 valence electrons on the free atom, minus 4 unshared electrons from the 2 lone pairs, plus half of the 4 half of the 4 shared electrons, gives me a formal charge of -1. Okay, so that's going to give me 0, 0, -1. In this resonance structure, now I have a carbon-oxygen single bond and a carbon-nitrogen triple bond. I've simply shifted the electrons around. I still have 16. Everyone's octet is satisfied. Going through the formal charge calculations, now we'll see oxygen has a negative formal charge, -1. Carbon has a formal charge of 0. Nitrogen has a formal charge of 0. If you want to pause the video and look at my calculations over here, please do so to see how we came up with those formal charges. In the last one, we'll switch the triple bond to the other side. Oxygen now is going to have a formal charge of +1. Carbon, formal charge of 0. Nitrogen, a formal charge of -2. Ugh. Okay. So now we're going to use our criteria to decide which of these is the most important resonance contributor. We're clearly going to rule out the third one because having positive formal charge on oxygen is not good, and having that much charge separation is pretty bad. So it's down to either the first one or the second one. The first one has a formal negative charge on nitrogen. The second one has a formal negative charge on oxygen, which is more electronegative. Oxygen. Therefore, we're going to say that the second one is the most important resonance contributor, with a formal charge of -1 on oxygen and formal charges of 0 on carbon and nitrogen. By the way, one thing I should point out that you'll notice is that the sum of the formal charges on all the atoms in the resonance structure is equal to the overall charge on the polyatomic ion or molecule. So we're going to say that this means that in the most important resonance contributor, the carbon-oxygen bond is close to a carbon-oxygen single bond. The carbon-nitrogen bond is close to a carbon-nitrogen triple bond. Okay, so is that true? Let's look at the actual bond lengths. In the cyanate anion, the carbon-oxygen bond length is 136 picometers, the carbon-nitrogen bond length is 117 picometers. Well, let's look at some carbon-oxygen and carbon-nitrogen bond lengths, okay? Look at that. The carbon-oxygen single bond length is 144 picometers, which is pretty close to what we see in cyanate. The carbon-nitrogen triple bond is 114 picometers, which is pretty close to what we see in cyanate. So the formal charge model worked in predicting that in this particular polyatomic anion, the most important resonance contributor is the one with the carbon-oxygen single bond, the carbon-nitrogen triple bond. Life is so satisfying when things work out like that. Okay, in our next video, we're going to talk about the three-dimensional geometries of molecules. See you then.